Okay, so this video is to help students who needed to see how to find the correct answers for their transformations test for Unit 1. In question number 1, Becky uses a transformation to go from the original pre-image trapezoid to our new image trapezoid K prime, L prime, J prime, K prime, L prime, M prime, and it says what type of transformation is this? Now, down here you see plastic, soft, elongated, and rigid. And a lot of students said, well, you never talked to us about this. Actually, I did. I used the word rigid. But let's reason out why it would be rigid. Rigid means stiff. It means it stays the same. Look at this trapezoid. Look really close at it. What do you notice? I notice that it's the same size and it's the same shape. It just slid over. Would plastic things stay the same size and shape? Or could I take something plastic and change its size? You know, like, I don't know, a plastic bag I fill up with water. Would it change size and shape? What about a plastic bottle if I squeezed it really hard? Would it change size and shape? It would. So it can't be plastic. What about something soft like a teddy bear? I know I can change its size and shape. I've stuffed a teddy bear inside an envelope before. What about elongated? Elongated means to stretch. No, that changes. But there's that word rigid, and rigid means not changing. And so the answer to number 1 would be D, because it stays the same size and shape. Number 2, which diagram represents a translation? Well, by definition, a translation is a slide or a shift. It's rigid, meaning the shape doesn't change. If it starts a triangle, it ends up a triangle. But not only is it rigid, it maintains vertices in the same position. Reflections flip things, and so they don't stay in the same position, and turns, rotations, turn things so that vertices don't stay in the same position. But if I called this vertex A, B, and C, then I would have an A prime, a B prime, and a C prime that are in the same position. So you can see that B was slid to the right, and that's 1. But there's another one that was slid. Not this one, A, not C, but D. So we're looking for A and D. Whoops. Both diagrams B and D, so we're going to choose answer D. Number 3, Melissa drew 4 diagrams of transformations. Which one represents a reflection? Well, remember, a reflection is a flip. If we reflected it, we flipped it. And so one of these shows that a diagram was flipped over a line of symmetry. So it's equidistant from that line of symmetry. It doesn't change its height or anything else. It just flips it over. The only one that shows that is A. B, C, and D don't show that it flipped. And so we're going to choose diagram A, which is letter A for our answer. Number 4. These quadrilaterals are shown. And we started with original figure or pre-image, and we ended up with a new image. And it says what sequence of transformations will make this shape here map onto the shape found to the right. Now, I'm going to be honest with you. To rotate means to turn, but when you turn around the origin. And so you have to like move. So you have to turn around a fixed point. So I'm going to take that away just because I want to show you that if you go from the center, from the origin, whoops, let me get my pen back. You're going to be equidistant as you turn. So that turn is going to go an equal distance from that origin. You see how D went an equal distance to its new point. Here it's 3 over and 1 down. Now it's 3 up and 1 over. but it's equidistant around a single point of rotation. So this one's a rotation, and it turns it to the right one turn. So let's talk about what right and one turn mean. Every turn is in 90-degree increments. And so one turn would be 90, two would be 180, and so on. We talked about that in class. And right has a name. We talk about clock. And when we turn it right, that's called clockwise. And if we take that same clock and we turn to the left, it's called counterclockwise. We turned right, so it's a clockwise rotation of 90 degrees. If you look down here, there's your 90-degree clockwise rotation, not counterclockwise, that would have been backwards, not 180 degrees, and definitely not reflected over these axes. So we would go with choice A. Number 5, two figures are graphed in the coordinate grid. Which statement best supports the conclusion that M is congruent to M prime? What makes them congruent? You have to look very carefully at each of the statements to see what they're describing. Statement A says that it was taken 10 units right and 1 unit down. So let's take this corner and go 10 to the right. And 1 down. Is there a figure over here? Do you see something I don't see? No, our figure's down here in quadrant 3. So it can't be A, because A is just taking us way over into space. Was it reflected? Well, no, because the x-axis is right here, and this one is 2 above it, and the other one is 1 below it. That's not equidistant across the line of symmetry, so it can't be B, because B is just not true. Was each vertex translated 2 units right and 8 units down? That might be possible. Let's take a look at that one. Let's take a look from this corner. Did we go over 2 and did we go down 8? We definitely went plus 2. Yep. And we went down 8. So what we've got is C. C is a true statement. D won't work because we definitely didn't turn it. Not around the origin. Whoops, I skipped a question. Sorry, guys. Let me go back. Let's look at number 6. On this one, you need to sort of work backwards. So we're given A, let me change that color, is -2, 4. And we know that A prime is -1, 2. How did we go from -2 to -1 and from 4 to 2? It looks like we divided by 2, which is multiplying by 1/2. Let's check that. Will that produce the new set of points? Half of -2 is -1, and half of 4 is 2, so that one checks. So I'm thinking that 1/2 is my scale factor, but let's check another point or all the vertices to be sure. -2, -2. Let's apply that 1/2 rule and see what happens. What's half of -2? -1. So both of those become -1, -1. Does that match? It does. Let's go ahead and check C really quick. C was 2, -2. Let's apply this alleged, what we think is the scale factor of -1/2 to it. When we do, we end up with -1, half of -2. Half of -2 is -1. That's the same as dividing by 2. Could have divided by 2 on each of these, you see? And does that match? It does. So our scale factor is 1/2. And that's one that you can show your work in the box. You don't have to give me sentences to describe it. So number 7. Rectangle ABCD has vertices of -4, 2, -4, 6, -2, 2, and D is -2, 6. If the rectangle is dilated by a scale factor of 2, what's the location of point A? So I'm looking for the new point A. I'm looking for A prime. Okay, so A is -4, 2, and I'm looking for A prime. I need those points. To get there, I'm using this scale factor of 2. So dilation is a multiplier. So what I want to do is I want to take my A and I want to multiply each of the points by 2. So 2 times -4 is -8. And 2 times 2 is 4. And so my new point is -8, 4, which is choice C. Again, showing your work will actually get you credit. You can show that. Number 8, the vertices of a rectangle are given. You can see that they're 3, 3, 3, 9, 6, 3, and 6, 9. If the rectangle is dilated by a scale factor of 1/3, which point would be one of the vertices of the dilated image? Oh my. So now we've got to take our points. I'm just going to make a little chart right here, a little row, column, whatever you want to call it. And I'm going to write them all down. And I want to dilate them by a scale factor of 1/3. So that means I'm going to multiply 1/3 times each of these numbers in the parentheses, which is the same as dividing by 3. So this becomes 3 divided by 3 and 3 divided by 3. So 3 divided by 3 is 1 and 1. Do I have an ordered pair of 1, 1 over there? I don't see it. So let's try the next point. Let's dilate 3, 9 by a scale factor of 1/3. That means 3 times 1/3 is 3 divided by 3. 1/3 times 9 is 9 divided by 3. So we get 1, 3 for our points. Do you see a 1, 3 over here on our choices? I don't either. That means I have to keep going. So now I'm going to say 1/3 times 6, which is 6 divided by 3. 1/3 times 3, which is 3 divided by 3. That gives me a new point of 2, 1. 2, 1. I don't see 2, 1. All the way down to the bottom. I got to do every one of these. So now I need to do 1/3 times 6, which is 6 divided by 3. And 1/3 times 9, which is 9 divided by 3. 6 divided by 3 is 2. 9 divided by 3 is 3. Oh, there it is. 2, 3. Had to do all the points to find it, but that's the one that would be one of the vertices of the dilated image. And again, showing your work, showing what I'm showing on the screen is how you can get your points. Because that's what you should have done to get the answer. Number 9. Triangle PQR undergoes a sequence of transformations which results in triangle P prime, Q prime, R prime, as shown in the grid. Which sequence of transformations can be used to map triangle PQR onto triangle P prime, Q prime, R prime? Let's box that. Okay, so now we're just going to have to look and see. It could be a reflection. Do you see how you could have reflected across the y-axis? Remember, when you describe a reflection, you always describe the line of symmetry. But I don't see that as one of my answer choices. I do see a reflection about the y-axis for point D, followed by a reflection about the x-axis, but that doesn't work, does it? So let's look at these rotations, because it doesn't make sense to reflect it over the x-axis. That would make it upside down. If I flip it, it'll be the wrong way. So let's take a look at these rotations. I'm going to kind of trace over my figure. It's not a pretty trace, but it's a trace. And if I turn 180 degrees, I'm going to do 1, 2 turns. It's going to flip it upside down. Now, when I turn, I'm going to go through quadrant 1. I'm going to go this way first, like this. And then that, point of rotation being the origin is going to put me over here. When I get there, I have to decide, am I going to follow it by a reflection about the, whoops. Sorry about that. That was not necessary. Am I going to follow it by a reflection over the x-axis or about the y-axis? Well, reflecting over the y-axis is going to give me a figure that's 2 units away that looks something like that. That's not going to work. So it's not over the y-axis. That's not going to work. So let's look at this reflecting over the x-axis. If I'm one below, let's see, if I'm 1, 2, 3, 4 above, I would have to be 4 below, right? Did I make my turn right? Let's look at that. Whoops. So let's go back and let's look at what happened with this rotation. I'm going to rotate 2 turns. So my first turn is going to bring me around here. And my second turn is going to bring me around here. So that's where I should have put my triangle. Because remember, we've got to have this, oh my goodness, really? We've got to have this from the origin, this center of rotation. Do you see? So if I started there and I turn it, it's got to come up here and then it's got to come over here. You see? And so now that I've done that and made it an equidistant point of rotation, now I've got to reflect it. So let's take it and let's flip it over. So now if I take it and I flip it, then it's going to go that way, right? Equidistant, because it was one above, so it's going to go one below for these points and so on. So yeah, A looks like it, really, Miss Hicklin? A looks like it fits. So we're going to circle A for number 9. Okay, and the last one, number 10. It says, Delia graphed triangle ABC on the coordinate grid as shown. She applied a series of transformations which produced a similar triangle that she labeled triangle A prime, B prime, C prime. What sequence of transformations did Delia use to produce triangle A prime, B prime, C prime? What sequence of transformations? Well, I'm going to tell you, but I'm going to look at it and I'm going to say, what do I notice? I notice that A has changed its location, and so has C, and so has B. So this had to either reflect or rotate. So it's something with reflection or rotating. And it's also bigger than it was before. So it either reflected or it rotated. We're not sure which, but something happened to make it change its vertex location. And it dilated. You guys are really good at these dilations, so you got that part. So let's look for the words that we're looking for. It's not a translation, so I'm going to eliminate A and I'm going to eliminate B because it can't be those. Okay? Let's look at C and D. Did my figure get larger or smaller? So ABC is the large triangle, so there's my pre-image. A prime, B prime, C prime is the smaller triangle. So when you reduce a figure, the scale factor has to be between 0 and 1. So look at this. Between 0 and 1. Oh, I thought 10 was the last one. I'm sorry, guys. You see? And did they reflect it? They did. They flipped it over. All right. Number 11, a triangle undergoes a series of transformations. Which transformations will result in an image that is similar but not congruent? So if it's not the same size and shape, the only one we studied that changes size is a dilation. Now, so it can't be A, it can't be B, it can't be C, but there's 2 dilations. How am I going to choose? Well, think about it. If the dilation is equal to 1, 1 times any number is the same. So 1 times anything stays the same, right? If I have $1 and I tell you, I'm going to multiply this dollar by 1, how many dollars am I going to have? Just 1. But if I do a scale factor not equal to 1, isn't that what causes it to enlarge? Whoops, enlarge, not enlarge, and reduce. Enlarge and reduce, it is. And so we're going to choose E. And then now we're at the last question, number 12. 2 triangles are shown. you have PQR, this little bitty one right there, and P prime, Q prime, R prime over here. Which sequence of transformations can be applied on triangle PQR to obtain triangle P prime, Q prime, R prime? Well, that one's really hard. So let's look at them. Our choices are rotating the triangle 90 degrees clockwise and then translating it. That's what A and B are about. And C and D say we rotate 90 degrees counterclockwise and translate it. All right, so let's come back up here and let's first decide, did we move clockwise or counterclockwise? In order for point P to go over here, we had to go in that direction, which is clockwise. So we know that we did a 90-degree clockwise rotation. Let's come back down to our answer choices. So let's strike out counterclockwise for C and D. That's not true. So we're going to get rid of them. So now we've taken care of the first part. Let's look at the rest. Did we go 2 units right and 3 units down, or 3 units right and 2 units down? Oh my, we're being very particular now. So let's take a look and see what happens when you rotate. First of all, when I rotate, you see how R is 1 unit away and 2 units up? It should be 2 units away and 1 unit up when I rotate it. So when I turn it, it's going to be there, there, and right 2 up, 2, right there. So that's my rotation. Now how far up and how far down did I go? It looks like I went down 1, and it looks like I went to the right 1, 2. It looks like I went right 2 and down 1. So right 2, there it is. No, that's 3 units down. Oh, did I count wrong? I did. Look at that scale. Silly me. I went from, hold on, let's clean this up. Too much stuff going on over here. Get rid of all that. All right, so let's rotate it. I'm at 1 turn clockwise. So since I was negative 1, 2, I'm going to be 1, 2, 1. No, I'm going to be 1, 2. So I'm going to turn right there. That keeps it equidistant. And so now I got to go down 2 and over 1, 2. Do we have a right 3 and 2 down? So there we go. There. Oh, I'm moving everything now. Lord have mercy. All right. So now that gives us B. So choice B. And there you go. That's it. Those are your test corrections for Unit 1.